Hi, my name is René Williams. I'm an assistant professor at the Molecular Photonics group at the University of Amsterdam. And today we will see how charges that are created with light, how they can recombine to form a neutral triplet excited state. This can be a so-called loss channel, the loss of charges, but it can also be considered as a new way to make triplet excited states. We will see that if a charge transfer state is converted into a triplet state, that this can occur slowly by so-called interaction of a nuclear spin with an electron spin, but it can also be quite fast and more efficient, proceeding by the simultaneous combination of spin-orbit coupling with charge recombination. So orthogonality of the nodal planes of the interacting pi orbitals, that plays an important role in this so-called spin-orbit charge transfer intersystem crossing mechanism. And we can correlate this mechanism to what we call the selection rules for triplet state formation, the El-Sayed rules, devised by Mustafa El-Sayed, an Egyptian. So this presentation is based on a tutorial review that was published in 2020 entitled Making Triplets from Photo-Generated Charges, Observations, Mechanisms, and Theory. Today we will discuss triplet formation by charge recombination. We will talk about the observations, the mechanisms, and the theory that is correlated with formation of triplet states. So if you put an electron-rich and electron-poor species together, and we excite one of them with light, we can get the formation of charges. We can create charges. Now, it has been a challenge for decades to use light to create long-lived charges. So either free charge carriers or long-lived charges, basically to convert the energy of photons into an electrochemical potential to, for instance, do reactions. Now, in a lot of this research, charges are often lost to form triplet states that are localized. So this has been an unwanted side reaction for years, and it's hard to avoid. And it also actually is occurring in organic solar cell materials. So here we see some interesting papers from Richard Friend and from Durrant, and they show the role of spin in these kind of processes. So you see that even the title, the role of spin and polaron pair mediation. So these papers are actually mainly focused on the slow processes on about a 10 nanosecond time scale. Now, if you have a closer look at this paper of Richard Friend, you can see that there's actually a lot of triplet already formed on a sub-nanosecond time scale. In fact, I discussed this aspect with Richard Friend in Groningen in 2013, and I asked him if perhaps spin-orbit coupling could play a role here. And I was quite surprised that Sir Richard Friend, who's absolutely top-notch in optoelectronics, he answered me that he never really understood spin-orbit coupling. So recently, let's say in the past, for me and for a lot of people, triplet formation by charge recombination was a loss channel. Now, recently, things have been reversed. We basically now see this method as a new way to generate triplets from charges, to a new way to make triplet states. And it has been gaining a lot of attention, especially in the last 2 years. So making triplet states, triplet excited states, is actually extremely useful, for instance, for photopolymerization, or to cure cancer with light and molecules, to kill bacteria with light, also for LEDs containing triplet emitters, and singlet fission. In singlet fission, it also plays an important role. So we have also observed this process even back in 1995. We saw that the fluorescence of this, what we call active fullerene diet, that was quenched by electron transfer, but still mainly a triplet state was formed. So that shows that the decay is the triplet. Even earlier in 1981, a Japanese photochemist, Mataga, and people, they saw even triplet formation by charge recombination occurring in about 40 picoseconds in a system containing pyrene and dimethyl aniline. And well, you can immediately see that these structures, this one was actually studied by Mike Wasilewski, a Porter Medal winner, and he came up with this fancy name. So for the fast process where you generate triplets from charges, they call it spin orbit charge transfer intersystem crossing, or the SOCT-ISC mechanism. So you can immediately see that these molecules, they have a common structural team. Basically, the donor and acceptor have an almost orthogonal relationship. A bit later, in 2013, we saw the same process, but actually in a film and with two different rates. So we saw that charges were recombining to form triplet states on a time scale of 10 to the 10 per second, a rate of 10 to the 10 per second, but also on a slow time scale on 10 to the 8 per second. So sub-nanosecond and multi-nanoseconds. So in film, we saw that charges were recombining onto a triplet state, and it was occurring with a fast process as well as a slow process. So, well, it could very well be that, was our interpretation, that there could be two mechanisms. And well, indeed, if you look into this process, then the slow mechanism is actually quite well understood, and it can be correlated to what we call spin dephasing, the so-called T2 star, the spin dephasing time, and it can be correlated to data of EPR, like the HyperFine coupling and the G value. So for this, we can estimate the spin dephasing time. And if we do this, for instance, for the radical anion of pyrene, we get this value here, 8 times 10 to the 7th. And it's very close to what we measured in our films for the slow process. So we can try to visualize this spin dephasing, and that's what we try to do here. First, we see here the electronic configuration of the singlet charge transfer state. This is the radical cation of the donor. This is the radical anion of the acceptor. And spin dephasing is basically an interaction of the nuclear spin with the electron spin. So if we start off with this singlet charge transfer state, this interaction can cause dephasing, so-called spin dephasing. And then we get into what we call the triplet charge transfer state. So here you see, of course, that an electron can not only be represented by an arrow, it also has a frequency with which it rotates like a cone. That's a model, just like the Larmor frequency that you know from NMR. So in this way, you can see that the spin dephasing converts the singlet charge transfer into the triplet charge transfer. And then charge recombination can occur fast because it's now spin allowed. And we get into a triplet state, T1, that can be localized on the donor, for instance. Here we see the electronic configuration. But we actually have to notice that this is one of the triplet states. So you selectively populate the T0. So if you go from a charge transfer state to a triplet state, you selectively populate the T0 state. And well, I will remind you that, of course, there are 3 triplet states, and in a magnetic field, we call them T plus, T minus, and T0. So either the 2 arrows are pointing up, pointing down, or pointing like that. So in that way, the mechanism, it sort of populates one specific sublevel of the triplet. And this is important for the spin dephasing. And we have seen that it correlates to a time scale of about 10 nanoseconds. Now I have to warn you, of course, if the nuclear spin and the electron spin, if they were very strong interactions, like for instance in phosphorus radicals, then the spin dephasing can be a bit faster, so on about 1 nanosecond time scale. So we have discussed what we call the slow mechanism, the spin dephasing, occurring on about 10 nanoseconds. What about this faster mechanism? Well, the faster mechanism, it is less known, it's less understood, but we can try to correlate it to the so-called selection rules for triplet state formation, the LCET rules, devised by Mostafa El-Sayed. So in molecules such as acetone and, for example, aromatic ketones, the n-pi-star transition of the carbonyl group, it can be viewed as the transfer of charge from a lone pair of the oxygen to the carbon atom. And this sort of exemplifies the importance of charge transfer in triplet state formation. So the orbital magnetic momentum is changed when the interacting orbitals are differently located on space, and thereby they can compensate for the electron flip. And so the LCET rules, they actually imply that this change of orbital configuration is very important. So for instance, going from an n-pi star to a pi-pi star, you have an allowed transition, which implies that it can be fast. So this is the LCET rules. Here are some examples of slow molecules, especially aromatic ketones are fast because they have this change of state. So expanding on the visualizations given us by Nick Turrow, we can try to exemplify these LCET rules with this. Basically here we have represented a pi-pi star state. So these are the two electrons, one in the pi and one in the pi star, represented onto the orbitals with this rotating cone method. And here we have the configuration of the pi-pi star singlet. Now, so if we flip this electron here, then we change the orbital configuration on one atom, and the electron ends up here. So here we have the electronic configuration, and you see that the electron in the n level and the pi star level, that they are in the same direction. So we form a triplet state. But again, you see that the spin orbit mechanism, actually, it's also populates selectively, well, either the T plus or the T minus. So with that, you can understand that the electron spin polarization is important as a method to prove the mechanism. So if you have hyperfine interactions, then you get the T0. With spin orbit coupling, you populate selectively the T plus or the T minus. So that with that, you can understand that from EPR data, you can have a final proof of these two different mechanisms. And people have done that, of course. So how can we correlate this to the so-called spin orbit charge transfer intersystem crossing mechanism? Well, basically, we can assume that this Hamiltonian can be considered as a 90-degree operator as well as an orbital overlap operator. And with that, you can try to visualize, this is also a picture from Turrow, that if you operate the Hamiltonian for spin orbit coupling, it is very efficient if it operates between a px and a py, and that is giving a higher value. So this implies that we have to put this picture onto the donor acceptor materials, and we have to optimize what we call the matrix element for spin orbit coupling. And so here this represents the matrix element that where you go from a singlet charge transfer state to a triplet state, and the triplet state can either be located on the donor or on the acceptor. So trying to visualize this spin orbit charge transfer intersystem crossing mechanism, we do this. So here we have again this singlet charge transfer state. This is the oxidized donor, this is the reduced acceptor, and it has a singlet charge, singlet character. So if we spin flip this electron, it goes, and it also goes to the donor, back to the donor, then you see that these orbitals are orthogonal. So orthogonal donor and acceptor systems, they clearly have a big change of orbital magnetic momentum, which can then compensate for the electron spin flip. And thereby we get again into a triplet state located, for instance, on the donor. Here you see the representation with the arrows. So this is what the electron that moved. And okay, in this case, it is drawn for the T plus. So you also see that in these donor acceptor systems, if you have an orthogonal relationship between the donor and acceptor, and they are quite close, then you selectively populate a specific sublevel of the triplet by this mechanism. And if you look basically with a what we call a frontier molecular orbital approach, then the charge recombination interaction is an interaction between a homoorbital based on the donor and a homoorbital based on the acceptor. So these are three molecules that are showing very efficient triplet formation by charge recombination. And well, you see that they have a very specific nodal plane orientation. So we not only need, it appears that we not only need orthogonal donor and acceptor systems, but also a secondary orthogonality of the nodal planes of the respective orbitals. And well, this is intriguing, but it's not, well, we still have to work on that. So if we do, if we want to make triplets from photogenerated charges, we have two mechanisms. One is fast, which uses spin-orbit coupling. The other one is slow, which uses HyperFine interactions. In fact, with ADF, with DFT, you can calculate this matrix element. So these are some first results on what we call the Mataga molecule. And you see that there's an interaction of about 2.5 wave numbers. And well, that's pretty large for our standards anyway. And so summarizing, if we want to make triplet from charges, if that is our goal, for instance, for photodynamic therapy, then well, you have better chances to get an efficient system if you focus on the spin-orbit charge transfer intersystem crossing mechanism, because that in principle allows faster rates if this matrix element, if you can optimize, if it's high. Of course, for a start, the charge generation has to be optimal and efficient, otherwise you don't have enough precursor. Also, so basically this whole process is mixed into a Marcus picture of theory of electron transfer. So also the charge recombination to the ground state, it is a competitive process, so that should be slow. Basically, the donor and acceptor should be close together. They should have a small distance. They should be virtually orthogonal, but in fact, if it is really 90 degrees, then the charge generation will not be so efficient. So it seems that about 60 degrees is optimal because well, some systems that we saw have that property. And we have this secondary orthogonality of the nodal plane. So that seems to be an optimal aspect. And furthermore, we can try to, well, have more grip on this matrix element for spin-orbit coupling, as we can probe it with calculations. All right. So I hope that you have understand a bit more about making triplet states from charges. And I thank these people for their contributions and you for your attention. In the grand scheme of things, we see that molecules can interact in the excited state, and these interactions can lead to different decay channels. One particular aspect of the Marcus theory of electron transfer, the decay of a charge transfer state into a local triplet excited state, it's a very complex and intricate process, and it can proceed by different either slow or fast mechanisms. And we can try to apply this fast mechanism to design new molecules for photodynamic therapy in order to destroy cancer cells with light. Thank you.